Okay, welcome to this continuation of last lecture where we're still in 6.1. I'm now gonna do the proof of change of variable formula or proposition theory 6.17. So that's where we start. The proof I will do is a bit different than the one in the book. I think mine is a bit more intuitive, but they share the same ideas. Before we get going, of course, if we can do the change of variable formula for non-negative functions f, then the general case follows by just linearity. So we can assume that our f is non-negative. Right. This is number one. And then just to gather some information here before, so we have the u and we have v, and they are open, and then we have this map u descending between them. Now, of course, another thing we can do is we can look at the set here with a certain distance to the boundaries, the uk being like, okay, so it has distance points which are further away than 1 over k to the outside. Now I get an open set whose closure is compact, right? And the image over here is also going to be something, it's going to be open, right? Because bijection sends open to open. So it also has a finite distance. Well, no, right. So the closure is compact. So then the closure, the bijection sends closed sets to compact sets to compact sets. So then the closure of this is compact, and so it also has a finite distance to the boundary. Okay, or to the outside of the set. So then we can call this corresponding set here vk. The point with this is, now if I can prove my formula for uk and vk, right? I do the change of variable there for non-negative functions f, then I can use the monotone convergence theory to just take a limit as k goes to infinity. What's the benefit of shrinking things inside? Well, if the closure is compact, and then the function exists there as well, right? And it's C1. So we can assume stuff that, so we're interested in this, right? And at some point we want to have something about the size of this guy, which, remember, now we use a funny norm, so this is actually easier to trace what this means. This is the supremum over all the columns, sorry, over all the rows of the corresponding sums. So on a compact set, here's a continuous function. On a compact set, it attains its maximum. So this thing here is you know, we can assume that this is less than or equal to some function m at all points that we work with. And likewise, I'm not sure we're going to need it. I think you do it in the book, but I don't think it's necessary. The inverse, since this also has a compact closure, then the inverse, you can assume that he's also bounded by some very large number m. Where it's not so important. We just need what this m is. We just need to know that it exists. Okay, so these are assumptions we can make. So now we just basically throw away this outer u and the v and just work on these smaller domains, right? So then life became easier. So now here is where we want to prove our theory. And what can we do then? Well, for example, I mean, what can we do with this knowledge? Let's say you have some set E here, which is of measure 0. Is it then true that U of E has Lebesgue measure 0? So this is going to be maybe something like this. Right? And the answer is yes. And how can we see that? Well, you know, the Lebesgue measure at the end of the day is defined by the Lebesgue outer measure. So we can cover this by some boxes that we call them Cj. So we have given epsilon, we can cover E by cubes, Cj, or rectangles or parallelepipeds, whatever it's called. such that the infinite sum of the Lebesgue measure of the CJs is less than epsilon, right? And then what is this going to give here? Well, the corresponding covering is not going to give me squares any longer, but this, how do we call them now? But anyway, so each one here is the derivative. Well, so these are U of corresponding CJ. And now you remember that what I proved last time, that if we have a bound like this, then I know that, you know, if I take an X and Y inside one of the CJs, then U of X minus U of Y is less than or equal to M times the side length of the CJs, right? That we call them L CJ. Yeah, because this is what I proved last time, right? We had this formula that, okay, so here we should have the infinity norm, and then this difference here is less than or equal to the maximum value of this derivative in the domain, or actually a line in between these 2 points will be fine, but since we now know the whole domain, so for all x, this is less than or equal to m, but so I can put here this m and then the distance between x and y in the infinity norm, which for a cube, so if x and y are inside of a cube, then the infinity norm of any difference between them is going to be bounded by the side length, right, of the cube. So that's how we get this formula. Now, if in every of these boxes I fix one yj, okay, then he's fixed, then this formula here basically says that all of the other u of x inside of that box has a distance yj in the infinity norm bounded by this number here, right? So here's u of yj, right, somewhere in the middle, and I know that all the other ones, they're bounded by this. So it means I can put a square here around it, right, which includes this guy, and what's the side length here? Well, it's bounded by this, but now this point became the center, so it can go both left and right. So basically, we can cover. So it will be 2 times this number, right? So what we see, so these cubes that we get from this process, we can call them the DJs, okay? And then we see that the Lebesgue measure of my DJ, well, that's just 2 times m times this. So this is the side length of the box as DJ, and then I raise that to the power of d. And then I get some constant here, just 2 times m to the power of d. And then the length of the box to the power of d, that's just the Lebesgue measure of the box, right? So here's a fixed constant. And here we know that when we sum all of these guys up, we get less than epsilon. So then the corresponding sum over our DJs will be less than this constant times epsilon. Since epsilon is arbitrary, we conclude that this formula holds. Yeah? So these are the prerequisites. So now I'm sending you back 1 week, at least in my time, because now I'm here like post-fixing the errors I made first time I did this video. So back. All right, so the first very nice trick here is the observation that it suffices to prove this. Yeah, so again, if I erase here a bit, it's a very neat. So inequalities are easier to prove than equalities, right? Well, we're dealing here with bijections, yeah? So then there is another function going this way, which you can call u minus 1. And now you have to remember a bit about derivatives. So, you know, if you take the identity function, I of x equals to x, then the derivative of that function is the identity matrix. Okay. But another way of writing this is u minus 1 time composed with u composed with x, right? So if I use I also for the identity matrix, this actually, think of this as matrix multiplication I of x, then yeah, it's all consistent here. And now we use the chain rule. So this identity matrix is u minus 1 derivative evaluated at u of x, and the derivative of that guy evaluated at x. So this is now, here's one matrix multiplied with another matrix. And now take the determinant of this guy, you get 1. So the determinant of him times the determinant of him is 1, right? So armed with that, let's say that we have this formula for all f's and for all changes of variable u. Well, then I can apply the same formula to the function f composed u and the change of variable u minus 1, right? Pulling me back from here to there. And that gives me another inequality going this way, right? So then I'm back to b.
And now I get f composed u minus 1 of y then again. And here you have the determinant. This is part of the function, right? So this I just have to write it. U prime, but instead of x, I write u minus 1 of y, just like I did here. And now comes this guy, but with u minus 1. So determinant, u minus 1 derivative at y, and then, yeah. Lambda of y.
Right, but then you see that this matrix times that matrix is the identity. You know, the determinant here and the modulus can go just on the outside. And now the determinant is multiplicative, so this here just becomes 1. So at the end of the day, I scrap this and I scrap these two as well, because that just gives me back y, right? So then I have back here, yeah? So then, nice, no? So it suffices to establish this inequality now. So we can assume f is positive, and if we prove this, then we're done. Now for positive functions, we can approximate them by a sequence of, this is lemma proposition 2, 1, 8, or 10, or something like that. So you know that there's an increasing sequence of simple measurable functions whose limit everywhere is your f. So if we call that sequence fk, then if we establish this for the simple functions, then you just use monotone convergence theorem on this inequality and you get it for f. So now we can assume that f is simple. But each simple function is just a linear combination with some coefficients and then some characteristic functions of measurable sets, right? So if we have for each measurable set this inequality, then by just taking linear combinations, we get the same inequality for positive simple functions. Okay, so then we have to prove this for any set A. And now I'm very pleased because last lecture we went through the idea of regularity properly. And I was like, you know, throughout the first part of the course, I was like, I wonder when I need regularity. And then that moment never came. And I was like, then what, is this even useful? Here, we actually need it, finally. So we want to prove this for any set A, but any set A is a very complicated thing to work with. So wouldn't it be better if we could work with simple sets A? But then you remember that you can always find, given A, we cannot find an identity here, right? But we can find So given any A, you can take an infinite intersection of open sets such that the difference here between A and this has measure 0. So let's write like this, A union E, where the Lebesgue measure of E is equal to 0. And now this allows us to say that, okay, I can assume that my A is actually open. All right. First of all, if I add my union E here, then the functions are different on a set of measures 0. So the integral is the same that we know from stuff in chapter 2.1. So then I can do my A union E here, A union E there, same here. I mean, here we have some function, right? But anyways, this and the guy that was here previously without the E, they are the same except for on a set of measure 0. Well, maybe we need to then show that U pulls back sets of measure 0 to sets of measure 0. And that is precisely what I argued in the beginning of this lecture 1 week later in my time, that it is true. So we can skip this technical point and at least 20 minutes of my mumbling and move on with the argument. Right, and now if I can do this identity for the V case, then I can use the dominated convergence theorem on this sequence and that sequence, take the limit inside, and I get my A, I get this guy, right? So then we can finally assume that the V case are, well, that set that we work with is open. So let's sum up this whole long discussion that V is a bad mutation. I have V and U here. Okay, so I'll get back to A and say that
it suffices to prove this for A.
Open. This is the conclusion of what I've said so far. What can we do with open sets? Well, we can take some sort of mesh grid here and write open sets as all of the squares that fit inside of my open set. We can start number them, yeah. So I call them R1, R2, R3, and so on. And then like that, I will fill up. Here, here, here. Yeah, but not on the edges, there will be a problem. But then I just do the same process with a mesh of half the size, and I keep, as soon as I find squares which are inside, I keep giving them the next name, right? So R15, R16, R17, and then I do it like that. So it's very easy to see that any open set can be written as a disjoint union of multi-cubes of varying size. And now we realize that if we do it for multi-cubes, then we're good to go again using just Beppel or monotone convergence theorem or what you want. But it has a catch, because if you just replace A by a multi-cube or rectangle, as I sometimes call them, that turns out, I thought that was what we were supposed to do. But that's actually wrong. Wrong, maybe it's not wrong, but it doesn't lead to a smooth proof. So we're gonna take the rectangle on the other side of U. Hang on, stay tuned for more action. Small correction. Be careful here with how one does things. So if A is open, then what do we have here? This is then the characteristic function of U minus 1 applied to A, right? You have your set A here, and then we take characteristic function of that and compose with U. Then you get on this side here U minus 1 of A, right? And I did this rectangular this decomposition into rectangles of this guy. I could as well have done that on this guy, right? Here's my grid thing. Then what will happen is I get here, this becomes rectangles, and here on this side, I now get U of the corresponding rectangles. Yeah, so U is a C1 function, so it maps open sets to open sets and all of that. And then, okay, then we repeat the whole argument. So it's fine to assume that this is actually a rectangle. Right, so do that in the book also, so I guess there's some point with doing it this way. So if we do that modification, then instead of having, and here we just get the characteristic function of that cube R, so we can just say an integral over R over what's left, the determinant, and here we get U applied to that R. Okay, so this is sufficient to prove. Now it got a bit ugly, let me write this nicely. All right, this is like a bad movie that just never ends. Now, suppose we were able to prove this with a 1 plus epsilon in front of here, while sacrificing, if for every epsilon, there exists a delta, such that as long as R has side length less than delta in every direction, then this formula is true. That's a weaker statement, so that should be easier to prove. Does the statement I had before I started fiddling here follow? If that's the case, well, if for every epsilon there exists a delta like that. So if R is actually a big cube, then I pick my epsilon, 10 to the minus 15. I get my delta. And now my R, I can chop it up into a finite amount of multi-cubes, which do satisfy this, right? And then I just use the summation here. So if I have for every cube which satisfies that, I write my big R as a finite union of such guys for each such smaller guy. I have this inequality. Then just by summing that up, I get it for my bigger R as well. So then this requirement is no longer in the game, and the 1 plus epsilon stands here, but now epsilon is arbitrary, and I can get rid of it. So it suffices to prove this statement. Yeah? Okay, so now if R big or small doesn't matter. So if I look at the closure of R, so I just add the right, and there was half open intervals we used to find it, but now I just close those intervals, yeah, so we can prove this formula for those guys. And now, what's this integral here? Well, this is a continuous function, because I probably never said that, but we need to assume that U is C1. So the differentiable, bijective, and the derivative is C1. So then the determinant is a C1 function. So now I have a C1 function in a compact set, so it assumes its minimum value and its maximum value. So this integral here is always bigger than it's bigger than or equal to, so 1 plus epsilon. And then I can replace this integral with the determinant of U prime of x min, let me call it. So the value where this gets its minimum, and then I just integrate a constant instead, so then I get lambda of C here. So I can always pick a point, yeah, because on a compact set, any continuous function assumes its minimum. We know that from analysis. Several variables, right? So then it suffices to show Right, so now we want to prove this. And since translations, the Lebesgue measure doesn't see translations, we might as well assume that this point is actually, I mean, so our R is sitting somewhere here, and the X min is a guy inside it, and 0 could be over here, but we can just take this and move it over here. And why not do it so in such a way that our X min ends up at 0? So then we want to prove that this holds true. Right, so I needed to structure this argument a bit better. So, right, we wanted to prove this, right? For all epsilon there exists a delta such that this formula holds. Where? So R is now a multi-cube with 0 inside R, because we said we have translation invariance, all right? And then R, what does this actually mean? It means, well, here's, we work with the infinity norm. When you write the norm on a set, you mean the diameter of the set, so the maximum distance between 2 points. Since we deal with a multi-cube and have the infinity norm, this actually just becomes the side length. So it is the side length of this R that should be less than delta. And then, since Lebesgue measures translation invariant, you can also assume that U of 0 is 0. So in the bigger picture, we had this big I U and the big I V, but then we took a rectangle inside it that we call it A, and here's U of A then, twisted shape. And then R is just a small rectangle inside here. And we say that, okay, we can move the origin so 0 is in it. And then we can move the origin here as well, so 0 is inside there as well. And then here's just a zoom out then of that guy. What is important to understand is I'm not allowed to really use, I cannot use like continuity properties at a point, because whatever epsilon, like at the point 0, in particular, because whatever epsilon and delta that works at 0 here, you need the same epsilon and delta is going to work for the neighbor, right? And then do a different translation. So 0 is always going to be at a different location. So there has to be some, when we get to the picking of epsilon and delta, we can't rely on that over only at the point 0. This has to have some, yeah, the 0 is going to move around here, right? So, yes, this is a difficulty. Anyways, so now here's R with the 0 inside it, and here's a twisted version of R. So this is U of R. Note that since the function U, since this is a very small set, right? There's no major difference between the function U of X and the function V of X, which I defined to just be the derivative times X, right? Because we know that U of X minus U of 0, but this is 0, is equal to U prime of X plus little ordo of, U prime of 0 times X plus little ordo X, right? And this guy is 0. So that one and this one, V of X, is almost the same. Now, if here I had V of X instead, then I would actually be done, right? Because this lemma 613 from last time tells us that if I have a linear transform here, then the Lebesgue measure of this is just the determinant of my linear transform times the Lebesgue measure of R. So then I even get it without this. So we're almost there, but not really, yes? So if instead of considering U of R, we consider V of R. What's that going to be? So 0 is here, let's say. It's going to be some sort of straightened out version of this. And clearly they're not going to differ much in the size. But the point is, as I go along the edges here, u of x is going to be maybe here, and then the v of x is going to be there, right? They're not that far apart, and if I could get some handle on how far apart they are, then I can approximate this guy with the corresponding one with the v there, which I know the size of. Okay, so what's the distance here between these two? Well, that's this order formula that we learned how to estimate it at the end of last class, no, beginning of last class. I told you, right? So let's recapitulate that. We have, so in our case, so u of x minus u of 0, which is 0, minus this guy. Okay, so this was the formula, right? How we come up with the quotient in the infinity norm of these two, when x, we assume x is less than delta, is less than or equal to the supremum of the difference here. Over again, here on the right hand side, assume that x is less than or equal to delta. Now, to get this inequality with the plus epsilon there, it would be nice. You see, the red guy is close to the white guy, but it's neither inside nor outside. Yeah, but we kind of, if we could make the red guy a bit bigger, so we could get u of r completely inside it, that would be nice. Yeah, how can we get that? Well, then we need a bigger square here, right? Whose image under, under the mapping B, or multiplication by u prime at 0, gives me a bigger set which includes this guy. Okay, but then what that means is like the pre-image, if I go back here and look at the boundary, the white, under the mapping B, I need to be inside here. So this means that, okay, if we go back, the inner red circle, if we go back with B, we just get the white smaller one here, and the outer red one goes to the outer red one. So this white one here is going to be something like this. So now I need to know how far am I deviating from the edge here to this point. Yeah. So at the end of the day, I need to study the composition of U with the inverse. So set S, sorry for my notation here, I don't know why this is a big S, but that's what it is. So that's going to be V inverse U of X, or U prime at 0 inverse times U of X. Right. So actually, this is the object I will be interested in. And now we're going to use this formula here on S instead. Now, what's S prime at 0? Well, here I get U prime at 0, and then the inverse of that, so that's the identity, right? Which is good. So the corresponding formula here tells me that S of x minus x itself. And this is what I want. When I go around here, I have some point x, and I want to know how far is S of x from x. No, I don't want any transform in there. And that's what I'm getting here. Now this infinity norm divided by norm of x infinity less than or equal to the supremum of, let me change variable here, so y such that y less than delta.
Right, so we have this. Okay. Anyway, yeah.
So again, d minus 1 is just this guy. Maybe I just confused you by introducing this notation d, I don't know. So now I'm going to write the identity, let me write over here, as u0 prime minus 1 times u0 prime, right? So matrix identity, because now this guy is the same as v minus 1, right? I have it here as well, so when I write the identity like this, I can pull this out. So this is supremum. So now let me write the full way. It's a bit longer to write it like this. So I have this times right. So now I have to stop and think for a while, but this identity is true if you have a matrix multiplication of matrix A and B, then whatever norm you use on it, one of these, whether you use the infinity norm or the 2 norm, the norm behaves like this, and that we see by looking at the definition. So you write the supremum, you know, this times that applied to all x divided with normal x, and then you just do a computation. So you see that it goes. Right, and now we have to use this, that guy is less than the value m I chose in the beginning, I think even last lecture. We said that, okay, both u prime and u prime inverse, right, this minus 1 and the prime can change places. And the u minus 1 and take the derivative of that is the same as the derivative of this, is just playing with chain rule. Okay. So this guy is bounded by m, and here, what do we know? So the definition here, it says, so now I need first I have a supremum in y, and I have a supremum in I, and then I have the sums. And here you have delta ui xj at y minus delta ui delta xj 0 to sum in j, right? So we have a concrete expression for how the matrix norm looks like. You can deal without it if you have the work with the 2 norm, but it's simpler now. You can really see it now. So each partial derivative delta ui delta xj is a continuous function. Continuous functions on compact sets, which we clearly are in that situation. I mean, this whole A guy, the boundary of it is well, the closure is compact and rigged it so that the function exists also in the closure, right? So if you have a continuous function on a compact set, it is uniformly continuous, meaning that given any gamma, usually we say epsilon, but epsilon is over here. So there. So now I say gamma instead. Given any gamma, I can pick an epsilon, a delta, such that this is smaller than gamma for any y, such as y minus actually whatever point here x, as long as these 2 points are not further apart than delta. So that applies this. So each guy here, I can make it less than some gamma, and then I have a finite sum and I have a supremum. So altogether, this whole shit, we can say that this is less than, we can make it smaller than whatever number, right? Up on choosing delta small enough. And this is independent of where this 0 is, right? Okay, now don't worry about this. This is just the old shit I was there. But right, so now I know that here. So S of x minus x in the infinity norm less than or equal to gamma times the norm of x, right? In infinity. And this tells me in turn, this is precisely what I want, right? Because now I have this, what I wanted, that I have control on how far he is. Yeah. So in other words, using the triangle inequality, S of x in the infinity norm is less than or equal to, well, the infinity norm of x plus gamma times the infinity norm of x. And this is precisely what I wanted. I know that if I just improve this one a little bit, so now the size is 1 plus gamma times my delta, then I completely cover this set, which is the inverse image under the linear transformation of this bit twisted set here. So this bigger rectangle here sits outside everything. So what can we do with this? Well, U of my R, right? That's the same as doing U prime at 0 applied to S of R. Because S, what it does is it sends the set through U, and then through the inverse of the derivative at 0, and then the derivative at 0, we send it back. So these two just cancel each other out. So we have this. And what should we call this bigger triangle? The red one. Let's call it R theta. So now, this is a subset of U prime 0 R theta. And look how beautiful. Now we are where we wanted to. This is something we can work with. And here we have subset. So this is also something we can work with. Now the Lebesgue measure of U of R is less than or equal to the Lebesgue measure of U prime at 0 applied to my R theta, which according to lemma 6 or proposition 613 is just the modulus of the determinant of U prime at 0 times the Lebesgue measure of R theta. But R theta is just a stupid multi-cube whose side length we know. So this is 1 plus gamma to the power of D times delta to the power of D, or in other words, 1 plus gamma to the power of D times the Lebesgue measure of R. And now we're done, right? Because what we wanted, is it still visible here? Probably, yeah. This one, right? What we wanted was to prove that this is less than 1 plus epsilon times this. And what we have is the left-hand side is precisely that. And here, God damn it. No, So I forgot to write here the determinant, yada, and then of course the determinant, yada, yada, should be there as well. And then it is what we want, just in a different order. And here, this guy, that's my 1 plus epsilon. So given epsilon, I can pick gamma small enough that this is smaller than 1 plus epsilon. And then that gives me my delta. And everything is independent of this picking of 0. And that's the end of this very difficult proof. I've never made so many mistakes in a video. I'm completely depleted. I refuse to do any more videos today. So now you get 2 videos, one for Tuesday, Monday, one for Thursday. We're going to go through this really slowly, but man, this is an argument with so many pitfalls. Incredible. I actually am humbled by going through this process. Right, but there you have it. Beautiful proof. Thank you and ciao.